Good morning. My name is Serena Yeung. I'm a PhD student at Stanford working...
That's your clicker if you want.
Oh, thank you. I'm working with Fei Li in the Stanford Vision Lab. And today I'm going to talk about some of our lab's recent work on scaling up video understanding. Let's see. So if we look at video data today, videos are everywhere. We have over 400 hours of video data uploaded to YouTube every minute. And if we look at internet traffic, 70% of internet traffic was video data in 2016, and this number is going to be over 80% by 2020. And we have video data in all kinds of forms. YouTube is obviously one of the most popular forms of video data. We also have a lot of video data in the form of TV. We have personal videos, such as GoPros, and we're also seeing more and more video now in scenarios such as smart spaces. So what's the current state of the art in video understanding? What can we do in video understanding today? So if we take a look at classification, we have things like the YouTube 8 million challenge now, where we're starting to be able to categorize about 5,000 categories at maybe around 15% top 5 error. So this is starting to get reasonably good. If we look at detection, so classifying the start and end time, finding the start and end time of specific actions in videos, this is a harder problem. And right now in videos, we're looking at about tens of categories, maybe up to low hundreds, where the performance is still pretty low. It's still a hard problem. So we're getting 10 to 20 mean AP, for example, at 0.5 overlap. Right, and then if we look at richer tasks, such as captioning, here we're still really just getting started. Right, we're looking at taking a video, writing textual descriptions of that, and here we're dealing with relatively still short clips, as well as pretty niche domains. So for example, here we have an example of cooking videos that we might be able to caption, but not moving very far beyond that. So if we compare this now with the state of the art in image understanding, let's take a look at that. So looking at image classification, we have the ImageNet challenge, where here now we're able to achieve greater than superhuman accuracy according to some benchmarks, where we're able to get very low top 5 error, and also the important part is that we're able to do a lot of transfer learning. So we're able to take pre-trained models, for example on ImageNet, and apply this to many new data sets, and be able to learn new models even with not so much data. Right, and then if we look at detection, again with image understanding, we're much farther ahead. We're looking at hundreds of categories, and most importantly, again, we're able to do a lot of transfer learning and fine tuning. So we're able to take some arbitrary data set that we want to do detection on, and when we can do a reasonable hope of trying to fine tune and get a practical usable model from there. And so this fine-tuning and transfer learning is something that I want to emphasize that has so far been much harder, and you don't see so much of it done with video data. And then if we look at richer tasks, for example, captioning in image understanding, we're now looking at dense captions, being able to write descriptions of very detailed regions in images, as well as also starting to form coherent paragraphs and telling stories about an image. And in image understanding, we're also moving even farther beyond that. There's been work on question answering, so recent interest in being able to ask and answer questions about images. So why is video understanding lagging behind image understanding? What is the gap here? And a large part of the problem is just the challenge of scale. Right, video data is a much larger scale in many dimensions. For example, if you're looking at labeling, it's much harder and manually expensive to acquire training labels. Then if you look at models, the added temporal dimension adds greater complexity. And then if we're looking at inference time, as well, just processing videos, right, to be able to do prediction is much more computationally expensive compared to images. And so today I'm going to talk about a few of our lab's recent works in trying to address some of these challenges. And first I'm going to talk about a method that's trying to tackle the problem of efficient inference in videos. So the task that we're going to address in this work is the task of action detection. So taking a video and trying to determine the start and end time of human actions in the video. So for example, here we have a video and we want to detect when someone is running and when someone is talking. And the approach that we're going to take here is this intuition that, well, in a lot of traditional video processing methods today, you do kind of a dense approach where you might, for example, extract features densely throughout the video and then process and analyze these features at multiple resolutions and multiple scales. But if we're going to think about how a person who's tasked with trying to detect an action in a video, for example, baseball swing, right? Well, if we want to do this in the most efficient way, how could we do this? We probably wouldn't watch the entire video densely and scroll through this. We might look at the beginning of the video and see, oh, well, this is a baseball game, so there's a good chance that there's a baseball video, a baseball swing here. And then we might skip ahead in the video, and at some point we see that there's a frame or a scene of people celebrating, and from here we can tell, well, if we see the celebration, there's a good chance that a successful, home run or some swing happened before that, right? So then we can skip backwards in the video and basically refine our hypothesis of where we think a baseball swing action happens. And then we can then determine the bounds of this action looking at much fewer frames and much more efficiently than looking at every single frame densely. Right, so this is the intuition that we're going to take. We're going to formulate this here as a reinforcement learning problem of an agent interacting with a video and tasked with predicting the start and end time of an action of interest. And so given video frames, right, at a given frame that we're looking at, we can put this through a convolutional neural network and look at the visual features from here. And from here at each time step, we're going to output both our current hypothesis that we have about where the action might be happening in this video, as well as the frame that we want to look at next. Right, so here I'm going to look at a frame a little bit more ahead in time. We're going to also use a recurrent network to integrate our understanding and our information so far that we've acquired about where the action might be. Right, so we're going to look at the next frame, again process this, the frame level features, integrate this into the recurrent neural network, and then continue. Right, we're going to now look backwards in time and do the same thing and continue in this fashion. Right, so at each time step, we're going to output both our current hypothesis as well as where we want to look next. And the problem with just doing this in this way that I've just described is that if we output a hypothesis at every time step, right, we're going to have too many predictions, obviously. And so what we're going to additionally do is also make this prediction of the detection optional. So we'll also have an emission indicator that's going to decide whether or not we want to emit a probability at this time step. And so training this model, we have differential components such as regressing to the start and end bounds of an action and the category of an action. And these are differentiable, and we can just train these using standard backpropagation. But here we also have non-differential outputs. So, for example, our outputs of where to look next and when to emit a prediction. These are non-differentiable, so we're going to train these using reinforcement learning, and in particular, the reinforce algorithm. And so doing this, training this model, we're able to achieve detection performance on par with dense sliding window-based approaches, but observing only 2% of the video frames. So just to give an example of the type of policies that we're able to learn, and so in this case, we have a policy that's trying to detect javelin throws in videos. And if you look here, this is the video frames that we have in the video, and the ground truth correct action is shown in gray up top. And so our prediction is in red. And what you'll see is that what the policy does is it is going through the video at a relatively larger intervals, taking relatively uniform but larger steps. And then when it sees an action starting to happen, it starts slowing down, right? It's now looking at more frames, and as it gets towards the end of the action, it actually goes backwards a little bit and refines its prediction before finally outputting with the red arrow a predicted instance. Okay. And so here I'll just show a video of this example that you just saw of the frames that we're going to be looking at. Right now it's going backwards a little bit in time, predicting the action instance, and then this is the video, and here this red box is showing that we're predicting the javelin throw. Okay. Let's see. Trying to move on. Okay. So, right. So this was an example of an approach that we're looking at into making video inference more efficient. And now I'm going to talk about a second work, which is now tackling a couple of these other problems on modeling the temporal dimension in videos, and also tackling the problem of trying to scale to larger numbers of actions. And so the task that we're going to tackle here is the task of dense action labeling, right? Where a lot of standard video detection approaches and data sets have focused on taking a set of actions that happen sparsely through a video or are sequential and happen one after the other. And we're going to now tackle the problem of, well, can we densely label this video? Can we, at every action, at every frame, at every moment in the video, label up to multiple co-occurring actions that are happening, right? So, for example, in this video, we can have basketball dunk happening at the same time as a jump is part of this, body rolls, and finally a basketball shot at the end. And so, first, in order to support this direction of research, we introduced a data set called multi-thumos, which extended one of the previously largest action detection data sets called thumos. And we extended this with dense multi-label action annotations for 30 hours of video across 400 videos. And so in total here we have 40,000 annotations, and we have a high density of labels per frame, 1.5 labels per frame on average, 65 classes, and up to, from 9 actions per frame, 25 actions per video, and 10.5 classes per video on average. And you can see examples on the left here of frames with multiple co-occurring actions labeled. Okay, so now if we look at how we can model these types of dense multi-label actions, well, several things to think about are that there's now going to be a high level of temporal dependency between these actions, right? And then if we look at standard action recognition models, for example, based on recurrent neural networks, all the state that we want to capture is in the hidden layer representation. And so we're always making a prediction of the current frame based on the current frame that we're seeing, as well as this previous hidden representation. So it puts a high burden on the hidden representation of these recurrent networks, or LSTMs. And so in this work, what we did was we introduced a model that we called MultiLSTM, which is an extension of the standard LSTM model to expand the temporal receptive fields of the input and the output connections. And so this gives the model more freedom in reading, right, taking as input a larger frame of inputs, as well as outputting predictions to a larger time period. And so if we look at the standard LSTM model, right, where at each time step we're usually always taking a single input and a single output, what we're doing now is expanding this temporal receptive field to multiple input frames. I've shown 3 here just for illustration, and multiple output frames. And then the multiple inputs and multiple outputs are aggregated using a weighting, and we use a soft attention type weighting for the multiple inputs. And we train this using a multi-label loss now for the multiple possibly co-occurring classes. Okay, so we basically showed that using this type of model and giving it this additional temporal flexibility allows this model to outperform standard LSTM-based approaches. And what it also allows us to do is to be able to retrieve sequential actions. So for example, here we have a basketball throw, right, followed by a basketball shot or a basketball catch, frisbee throws and catches. And we can also retrieve co-occurring actions. So for example, dives with a body roll or without a body roll, or you know, or sitting while talking versus standing and talking. Okay, so this work was addressing these challenges of trying to model temporal relationships and also trying to push the amount of actions and categories that we can handle in a video. And so the last work, the third work that I'm going to talk about, is now going to push in this direction of how can we deal with manually expensive training labels, right? Even though we spent all this effort collecting this data set earlier, it was pretty expensive to do that. It took a lot of time and effort labeling. So as I was mentioned before, labeling videos is really expensive. And this gets even worse when you're trying to label spatial or temporal bounds of videos. So given that, how can we practically learn about new concepts in video? Well, one idea is that web queries are a good source of noisy video labels. So you can search something like taking a selfie, and you can get all of these search results back. But the problem is that they're really noisy, right? So we get some examples of videos of taking a selfie that seem like they would be good training examples, but at the same time, we're also going to have videos of a woman, you know, I think falling off a bridge after taking a selfie, right? A news report, or we're going to have a video of Manny the selfie-taking cat, right? And so these are probably not going to be very good training examples. And in contrast, image search is much cleaner. So if we're going to do an image search for the same class of taking a selfie, we can actually see that, you know, we're probably going to have a good hope of learning something from this, right? We have already pretty clean examples here. So the problem that we're trying to tackle here is, can we efficiently learn from these noisy web queries, right? And our approach that we're going to take is we're going to try and take a reinforcement learning based formulation here to learn a data labeling policy, where we want to learn a policy that, given a small amount of label data that we do have, our data labeling policy on web search query results can do a good job. We want to do a good job on this reward set that we have, and if we can do that, then hopefully this can then extend to new classes that we haven't seen before. And an important problem here is to balance diversity with semantic drift, right? We want to be able to achieve a diverse set of training examples, hard examples, edge cases that we can learn from. But at the same time, if you have a lot of diversity, you start getting into the danger of semantic drift, right? Where you might drift into an entirely new category and then start changing your whole seed and idea of what this concept is. Right, and so our hope is that by using this reward set that we have of labeled data that we can evaluate classification performance on, that if our policy is able to do a good job for a lot of classes on this reward set, then hopefully it can do well for new categories not in that set. So an overview of our approach, given a new class that we want to train a classifier for something, for example, boomerang, we'll go to YouTube and we'll get candidate web queries from that. So here we just use YouTube autocomplete, and we'll get things like boomerang on a beach, boomerang music video. And then this is fed into our agent, which takes as its state representation, basically a representation of all of these videos, as well as a state representation of the current classifier that it's training. And I'm not going to go into the details of the state in the interest of time, but basically takes the state representation, and from here it's going to take an action of choosing a new set of videos, a candidate web query, to add to its current set of positive video examples, right? And it's going to label these as positives and update its classifier based on this newly added set of positives. And it'll always use a fixed negative set of videos that we just take from randomly sampled videos. And as I mentioned before, the reward is going to be determined from taking our current classifier, evaluating it on a reward set that we have for classes that we know, and then this will be the training reward of how good was this and how helpful was this this new set of positives that we just added. And so we'll train this policy on a set of classes that we do have labeled data for, and then at test time we'll take the policy and then apply it and deploy it to novel classes that we haven't seen before. So we train this policy, and if we look at the types of policies that it learns, well, for a fine-grained, uncommon class like netball, we'll see that if we just do a standard greedy classifier type approach, right, where we take our initial, let's say, group of seed examples that we have, and we go and continuously try and get YouTube query results that are most similar to our current seed examples, we'll see that it's getting very similar queries, right? Very visually similar videos that aren't going to be so helpful in expanding the training set. And on the other hand, what our policy does is it ends up selecting a bunch of videos of netball in different environments, in different scenarios, and so these will actually be more helpful training examples. And if we look at another example of bobsleigh, we'll see that this time what the greedy classifier does is that it first gets some bobsleigh videos, but then it starts, it chooses an example of, I think some Mario video game bobsleigh example. And after that point, then it does, it exhibits this problem of semantic drift, right? It starts just collecting a lot of these video game examples, which are not really the useful examples that we wanted from our seed. And so what our model does in contrast is that our policy also does end up picking a video game example at some point, but it's able to balance this desire for diversity and drift more. And so it's able to recover from that and continue to pick useful bobsleigh videos. And so we also applied this to novel classes, and so here's an example of taking a selfie, where we'll see that the greedy classifier gets many similar examples of taking a selfie, whereas our policy ends up choosing examples of taking a selfie in different environments, such as, there's one here with a tornado or underwater. Okay, so right, I've talked about three of our lab's recent works on addressing these challenges of scale with working with video data. Right, so I talked first about tackling this problem of efficient inference in video, and then about tackling modeling temporal dependencies in video, and then finally about trying to learn about new categories with few training labels. And so I think interesting directions for future work as we continue to tackle this problem of scale with videos is continuing in this direction of learning to learn, right? Learning these policies, for example. I showed an example of how to label data, but these types of policies that can help with reducing manually expensive, whether it's data labeling or training models. And I think related to that is also the problem of unsupervised learning, which is really important in videos where we have so much unlabeled data that we have accessible to us, but it's really expensive to obtain manual labels for these data or really any kinds of labels. And so unsupervised learning, I think, is a really important problem for the video domain. And then finally, I think as we're building up our capabilities in video understanding, it'll be an important problem to be able to organize all of this information and find relationships in this, and basically to be able to build up kind of a knowledge base of the dynamic visual world. And okay, so I just want to thank my collaborators, and I'm happy to take any questions. Yes. Yeah, so the question is, one of our videos that I showed was running from one perspective. Another was javelin throw from multiple perspectives. How does that affect training? So we don't make any assumptions on our videos or our data. So at training time, it sees these types of different perspectives. And you can imagine with enough training data, hopefully it's learning still what's the beginning of an action from different perspectives, what's the end of an action. And I think a lot of what our model is doing is reasoning, like looking for these types of keyframes or moments in video and trying to integrate this information together and analyze based on that. And so it's in that way it's able to learn and still make predictions from these different viewpoints. Yeah, question.
So how do you provide the feedback if your training data set is normal? How do you provide feedback on the results?
So the question is, do you mean during, what's the reward during training?
No, I mean, you need to provide the feedback for the analysis process. When the results, feedback is wrong.
Okay. Yeah, so the question is, when we're doing this process of efficient video inference, how do we provide feedback of whether it's right or wrong? And so this is since we were formulating this in this sort of a RL type of setup, our feedback is in the form of a reward. And so what we have is we output a prediction at any, whenever we emit a prediction, we'll then look at the overlap intersection over union with the closest ground truth label from a video. So we have labeled start and end times of all actions in the video at training time, and then we'll say that if there's sufficient overlap, we'll consider this correct and incorrect otherwise. Yeah, question? Yeah, so the question is, how is the data and the training for the efficient video inference conducted? And so what we do is the video is labeled with, we have videos with temporal start and end times, and then we're going to train on chunks of video, right? So we have in our training batches, we have all these different chunks of video, and then every time we pass this through, we basically will get a trajectory of the current glimpses that are being taken, and then the supervision comes from this reward, which is what I was just describing of how much overlap there is with the nearest ground truth. Okay, thank you.